So welcome everyone. Welcome to our unusual 5th July lecture in physics held in August. My name's Susie Shee. I'm an associate professor here in accelerator science, which will become very relevant this evening. I'm also the curator of the July lectures in physics. So it's a great honour to have here not just our regular and new members of our July lectures in physics audience, but also in the front here we have a lot of people who've been celebrating the 50th anniversary of one of our particle accelerators here in the department. So before we get going with tonight's event, I'd just like to recognise the lands of the Wurundjeri Woi-wurrung people on whose lands we're holding this event tonight, and pay my respects to their elders past and present. Anyone coming in late, please come down the front. There are seats reserved down here for you. Thanks. So tonight's lecture is called The Science and Stories of Melbourne's Particle Accelerators, and as a relatively new academic in the school, but one who is leading that field here of particle accelerators, it came as a real surprise to me when our speaker tonight did a deep dive of the research and came out with all the stories he's going to tell you tonight. But the main event is Adam, and so it gives me a great delight to introduce, as David Jamison did last week, his former PhD student. Our speaker tonight, Adam Steinberg, was actually my former PhD student, and I think he might also be the youngest ever person to give one of the July lectures in physics since it started in 1968. Challenge me on that if you have more information, but I believe he may be the youngest. So Adam Steinberg is originally from the UK. We actually met when he was doing his undergraduate physics degree at the University of Oxford. And I'm pleased to say he took an interest in particle accelerators from that point in his career. And he did his PhD actually on a joint scheme between the University of Manchester in the UK and the University of Melbourne here in Australia, which is one of these wonderful joint mobility schemes that enables the sort of collaboration and internationally leading research that this department here is so well known for. So Adam completed his PhD just last year in 2024. And he was actually the recipient of one of the premier prizes in accelerator physics, which is the Mark Oliphant Prize for Outstanding Early Career Researchers, which he received at a big international conference earlier this year. I think I've embarrassed him enough. He is now a research fellow in the heavy ion accelerators facility, which the people in the front will know very well, and works on one of our accelerators here, the one that is currently celebrating its 50th anniversary, and I'm sure he will tell us all about it. Adam, over to you. Thank you.
Evening, everyone. Thanks, Susie, for that introduction. So this evening, many people who are here tonight, and by the way, everyone who's just kind of walking in the back, please come. There are seats for you right at the front where we can all watch you walking in late. It says reserved if reserved for you, so please do come. There are many more seats here than there are scattered around the room. So many of you are here tonight celebrating the 50th anniversary of the Pelletron. It's a particle accelerator that's really driven a lot of the research of this department throughout its lifetime, and throughout the lifetime of the department in this building. Well, not this building, the building next door, but the building it's in currently. Because really, the department was built around the accelerator. The department moved into this new building, I guess it was called New Physics, but it's now called David Carrier Building, in 1974, and the installation of the Pelletron happened at the same time. And we'll see actually during this talk that quite a lot of accelerator stuff happened kind of around this period. And in one early version of this talk, I was saying things at great length about the Pelletron, and then I realized, given how much of this audience is going to be the people who actually are the experts on the history of the Pelletron, it would be a very bad idea to tell stories that they could tell better than me. So instead of talking only about the Pelletron and all the amazing science that's driven, instead we're going to be exploring the broad range of accelerators that have been here in this department. It's not just been really 50 years of accelerators, but, well, we'll see during this talk, it's been many, many more years, and it's driven a broad range of research and, well, it's a crazy number of projects, PhDs, master's students, honors students, postdoctoral fellows, and many careers have really been inside the accelerators of this department. But if you're only interested in money, there's that too. Because And I've taken a quote here, which you can obviously read for yourselves, but the annual market for all medical and industrial accelerators, a lot of which look a lot like the accelerators we have in the physics department just next door, is $5 billion a year. Now, that's not $5 billion a year of things that people do with the accelerators. That's $5 billion a year on the accelerators themselves. Because these accelerators are powering the semiconductor industry. They're powering cancer treatment. They're powering the chips in your phones. They're powering almost all of society. So it's not $5 billion in sales or in things they produce. It's $500 billion. And this was some years ago, and we've all seen inflation in the last few years, so I imagine it's probably at least, I don't know, 50 or 70 or 100 times more than that now. But accelerators are big business, but they also kind of started small. They drive research in a broad range of areas. We're going to touch on a lot of these during this talk. You'll see as we go, there's been nuclear science, which was a lot of this department for a long time. There is looking at art and whether it's real or fake by looking at the elements inside of it. There's medical and biomedical research, and there's also chip manufacture and checking and things like that. But first of all, a question. Is this a particle accelerator? Probably you're thinking this guy's lost it, let's go straight to the drinks, because clearly there's not much of interest here. But actually, if you think about it, if I throw the ball, and I was originally going to throw this ball, now I'm looking around me and seeing lots of very delicate things, so I think actually I'll just gently put it down. I was going to throw it quite fast. But if you think about what is throwing or hitting a tennis ball, I reckon, I'm not very good at these things, but it's about 100 grams worth of tennis ball, give or take, and I reckon I could throw it about 10 meters per second. So that's 5 joules of energy, which sounds like a big number if you don't know what we're talking about. But within a tennis ball, much like this one, that's a 5 with 23 zeros after it, number of atoms. So there's quite a few individual atoms inside a tennis ball like this one. And so per atom, that's 1 with 24 zeros in front of it, worth of energy that each of those atoms has, which really isn't very much at all. If we want to probe the secrets of the atomic nucleus or discover new fundamental particles, a 1 with 24 zeros in front of it isn't going to cover it. And also, obviously, a 1 with 24 zeros in front of it is quite a long thing for me to keep saying all the time. So instead, let's try to introduce a different unit system, which we'll be able to use to translate how powerful these particle accelerators are. So rather than this tennis court and this tennis ball, which I'm going to put down here so I'm not tempted to throw it during the lecture, instead, let's imagine just a positive and negative plate, like a capacitor setup. And we put on there 1 volt over the 2 plates, and we have an electron generated somehow near the negative one of these. And of course, as we all know from high school physics, that electron will be pushed away from that plate towards the positive plate. And we call the amount of energy that the electron gains while traveling from that negative to positive one 1 electron volt, which is a very small number when you look at it in terms of number of joules per electron. But when you compare it to that 1 with 24 zeros in front of it, it's already 100,000 times larger. So me throwing a tennis ball, it turns out I'm actually not as strong as I thought I might be, because just such a simple setup. 1 volt, which a battery is more than that, and 1 electron, well, they're all over the place, can be 100,000 times more energy than anything I could produce by hand. But this is all very nice in theory, this idea of shooting electrons out of stuff, but it doesn't actually work. And that takes us to the first of the demos we have here tonight. This here is a cathode ray tube. You can see on this side is where the electrons will be coming from. There will be some voltage coming from here. There's a positive anode there. The electrons are going to come from back here, and you can see it in the image behind me too. I'm not going to point at it because people online will be able to see that. And they'll be shot off towards this big bulb thing here. And so let me find the right switches. Let me turn on the power supply, and we'll see. I mean, kind of it's very awkward if it didn't work. But very simply, there we are, there's me behind now. You can see a faint blue line there. I'm hoping it's pretty clear. I'm not sure how easy we can see that on the camera. I don't think I can turn it too much, unfortunately. I'm turning this to there. Yeah, that's a bit more clear, isn't it? Great. Good. Oh, now it's getting dark. There we go. It's much more dramatic now. You can actually see what I'm talking about. So we can see coming from over here, there's some sort of beam of particles. These are electrons. They're being accelerated right now through 5 kilovolts. So that's 5,000 volts. It's 5,000 times more than the number we had before. So they're gaining a fair bit of energy. That's pretty good. And I can stand right here and it's totally safe. I'm not irradiating myself. I don't need to go get treatment for this. They can't get through here. We checked. And there's also just a bar magnet here. So we know that we can accelerate these particles, but can we actually control their motion? Can we control what we do with them? And you won't be able to see it too well on there, I suspect, but if I grab this magnet here, you can see it bends. I mean, it's very simple, very obvious. It bends, and if I turn the magnet around, so right now is the red side pointing towards the particle beam. If I turn that around so the blue side is pointing towards the beam, do we think anything will change? Will the same thing happen again? It goes the other way. Good. Most of us did some physics. And now under here, I've got some much stronger magnets, which are really quite heavy. So if I use these much stronger magnets, will there be much difference? Well, let's find out. And it goes a lot further. In fact, it goes all the way off. And if these magnets were strong enough, and if they went the whole way around, then we could get these particles, these electrons, to travel in a circle. And you can see, potentially in the room, how far I am holding this magnet, and it's already turning, which is part of why this magnet is a bit more scary than the other one. So I'm going to put this back here before I hurt myself. You heard that thunk? That could have been my fingers. But it wasn't, but we did the risk assessment. So we see here kind of two of the main, most important concepts in accelerator science. And almost all the particle accelerators we'll explore for the rest of this talk. We've seen that we can produce electrons and accelerate them, and that's true of protons too, with slightly different methods, but we can produce our particle beam and give it energy in very, very simple ways. And we've also seen that with just magnets, and I'll pick up the weak ones again because they're much less scary, we can bend our beam from side to side. And if they're strong enough, we can get them going in a full circle and control the motion of our particles completely. So now let's move on from our demo. There we go. And start looking at some of the bigger particle accelerators we've had in this physics department. I'll make sure I turn this off, otherwise we'll run out of electrons. Well, that'd be really bad, wouldn't it? But let's talk about some of the physics we actually do with these accelerators and the accelerators we have, because we don't just have these tiny 5 kilovolt machines. We have had many particle accelerators in the history of this department. And one of the main things they drove over time, in fact, I would say the vast majority of the science research program we've had on particle accelerators here has been under the umbrella of what you might call nuclear physics. There have been various different aspects of that over time, and many people in the audience joining us tonight who are the alumni who have worked with the Pelletron, worked in some aspect on nuclear physics. And Melbourne's first particle accelerators, and I'm afraid there's a picture of one at ANU because I couldn't find any of the Melbourne one, sorry. But they weren't machines looking like this, and they weren't huge, kind of massive things. They were also probably smaller than this one, although I can't prove it without the photos. Instead, they were, well, they looked a lot like this, but smaller. They were the Cockcroft-Walton voltage multiplier. And it reached the quite large energy at the time of 0.2 megavolts. So if that was 5 kilovolts, this is larger than that by about 100 times. Someone check my maths. Now, why were we building these accelerators? Mostly it was for deuterium and neutron scattering experiments. These, look at the year, this would have been in 1938. So think about what we knew about the universe in 1938. We knew there are atoms, we knew there are various particles, we knew what was going on with them, but we weren't really sure what would happen when you smash things into each other effectively. And so using this relatively small accelerator, at least by today's standards, we were able to probe what would happen when you scattered deuterium and neutrons off each other. And just for reference of Melbourne being at the forefront of accelerator science, not just now, but even then, this kind of accelerator was invented in 1932. So only 6 years later, they were building the first one here, and it wasn't just going down to your local Bunnings and picking one up and building it, or IKEA, where it's kind of flat pack and you try to put it together and there are 3 screws missing, and you've got an extra pillar for some reason. Instead, this was all built in-house, using our own workshops, using our own technicians, using our own students, staff, and scientists. And also bear in mind, it seems like 6 years might be a long time, but this is all totally new. And having come over from the UK to here quite a few times, the flight feels like quite a long time, so I can't imagine how long it took to get the information over in 1932. And so here's just one example of the many papers that came out of this particle accelerator. They've got kind of grand, exciting titles like Scattering of DD Neutrons by Deuterium. And then you get kind of lots of graphs like this, where papers today tend to contain lots of kind of very bright and exciting graphics. These feel much more sober and serious, theoretical distributions. But this was basic science being done in this physics department in around 1938 with their first particle accelerator. In fact, it was so successful that they built another one only a few years later to supplement the research program. And, I should say, these accelerators are still used as the first stage of larger facilities today. Because you can imagine if we want to get particles to, let's just call them stupendously high energies, we can't get there from nowhere. Instead, you need to produce them somehow and give them some initial kick. And you can use accelerators just like this to produce that initial kick. For example, in Japan, in KEK, which is huge, there's a 750 keV version of this. So it looks pretty similar, actually, to one I've got there from ANU, except they're still using it today for their kind of exciting and very much modern, at the forefront of particle physics, accelerator facility. And so let's maybe start adding some items to our timeline. We've got the Pelletron, which is the 50th anniversary. And then we've got this Cockcroft-Walton accelerator, and the two of them that I mentioned much earlier on, in around 1938. But what about electrons? So the Cockcroft-Walton can produce protons and positive ions, but it can't produce electrons. So what if instead we wanted to get beams of electrons? A bit like we can produce from our cathode ray tube here, but obviously higher energy and more useful for, say, nuclear experiments again. And going through the various archives and loads of old theses in our physics department, I came across this one example of a thesis, the acceleration of electrons and the scattering of positrons and electrons from 1950 by W.B. Lassick. And I'll say as an aside about, actually Mr. Lassick, Dr. Lassick, after he submitted this. I have no idea what his first name is. I've read through his thesis, I've searched him online. He only ever referred to himself and his colleagues at the time only ever referred to him as W.B. Lassick. So if anyone here happens to have ever met or known or anyone around Dr. Lassick, I'd be really interested to know what his first name was. But we do know what he looked like, because in the front cover page of his thesis, well, actually, I should say, we know what someone looked like who he wanted to include in this thesis. It could have been anyone. but I assume it's the man who became Dr. Lassick. This is 1950, so he's wearing a tie and looking very serious and a bit demure. I think you might call that smoldering today. But this was him. He was doing his research here, in amongst a whole wide range of other people too. Even at this time, it was a bit of a big ask to make an entire particle accelerator entirely by yourself. So how did they actually make their electrons? How did they accelerate their electrons in their early particle accelerator? Well, they used electromagnetic induction in order to do it, which brings us to our second demo, because nothing like a good demo to show off ideas that are easy with nice, cool things to show. So maybe we can get the camera on this as well, and hopefully it's a bit better position for there. Otherwise, I'll move it. But what we have here, there we go. Amazing. So, I think that's a good height. So we have here, a transformer. So we all know transformers from our houses or from at the end of the road. The boxes that are always buzzing. And in fact, I don't know how well we'll be able to hear it in the room, but if I turn this on, if I go right up here, that's humming quite a lot. So there's a transformer in there. The back of it here says either 220 or 240 volts, 50 or 60 kilohertz. So it's very flexible. Probably can do more things than I can. But all we're doing here is having current going through our transformer and creating a magnetic field that changes in time. And that change in time path is important. Now here I've got some very suggestive, I'll put it on the camera there, some very suggestive metal rings. I've got a few of them. I'll maybe use this one and this one. There's a thinner one and a fatter one. I'll start with the thinner one. we've got our strange humming transformer, and the metal ring that I've just placed on the bottom. Obviously, I'm going to press the on switch, and something's going to happen. Because if nothing were going to happen, I probably wouldn't do it. Any guesses? And probably many of you have seen this before as well. But any guesses what will happen when I press the on switch on this transformer? Oh, God. Yeah, good. I've done lots of practice catching these. And so let me do it again, just showing it works really well. If I do it again, didn't work that time. And you can hear it's working because it really hums. Anyone have any idea why it didn't work that time? Because obviously there's a gap in this ring. So I tricked you all. But no, this one, hopefully, still works. And then let's get a bigger, thicker, put it down here, a bigger, thicker, heavier one. Because it's bigger, it weighs more, obviously. I can't prove this to you, but I can say it. So if I put the thicker and heavier one on, how's it going to change? Will it go lower, probably reckon? No, much higher. I reckon on the camera you can't really see how much higher that was, but hopefully people in the room can attest how impressive my catching skills are. And the reason it goes much higher is because the ring is thicker. So it induces a larger current in this ring, which I'm showing on the camera there. And the current is larger, the forces are larger, and so it gets shot up higher. I'll do it one more time, although I recognize I'm really testing my luck here. Not dropped any of them yet. Very good. Thank you, thank you. So what we've seen from that is that we can use magnetic fields that are changing in time to impart some sort of force onto, in this case, a metal ring, but obviously there are also lots of particles inside that ring, and so we can use this magnetic field that changes in time to give energy to our particles. And that's basically the concept behind the next particle accelerator that was produced here in the University of Melbourne Physics Department. Now, why? Why were they doing this? Why are we here tonight? Mostly they wanted X-rays for nuclear experiments. They wanted to see what happens when you shoot X-rays at atomic nuclei. How do they disintegrate when you put these photons on there? You've guessed it, photodisintegration. And how do we produce these X-rays? Because I said it was an electron accelerator, so where are these X-rays coming from? It's very simple. You shoot an electron at a target, in this case made of something like tungsten, and a photon comes out, more or less just by conservation of energy. So we can produce X-rays from our electron beam pretty easily. And when did they do this? I mentioned this 1938 Cockcroft-Walton accelerator. Well, the first betatron, contrary to what many of you may think, isn't the Siemens betatron up on the podium, which we'd have seen as you walked in, or we might see later on. In fact, it's from 1947, this 2.8 MeV betatron. This is from work by Lasix, the guy with the smoldering look from before. And you can see a couple of interesting features on it, which I just want to highlight. Bear in mind, this is all made in-house. They didn't buy this from somewhere. They didn't, as I say, go down to a shop and get the parts. They built this all in-house. So this here is part of the vacuum system, because obviously, as we saw with the electrons from earlier, if the beam was just in air, it would be absorbed very quickly. So this all needs to be under vacuum. Today, vacuum systems are a little bit more modern than just flasks. But back in the day, that was good enough. And then up here, this is the area where the electrons would have been circulating. They're traveling around in a circle with magnets above and below them, gaining energy from a machine which was kind of acting a lot like the coils of this transformer. Oh, but my picture's gone. But that's all right, though, because in the Physics Museum, just upstairs, we have the original donut, which I'm going to very, very carefully lift because it's from 1946, and it'd be very bad if I dropped it. So this here, which was a donut there, is made of glass. You can see by my left, your right pinky finger, which I'm holding up there, there's a bit of a small gap in the tube. This is where they would have been keeping it under vacuum. Then further on down here, there's a kind of a plug-looking thing. This is where they would get the power from, and the electrons would have come from here to be injected. Then they travel round in circles, around and around and around, inside this donut, until they are made to hit that metal target. This was all made in-house. That paper I mentioned before goes into great detail about how they went about producing this. I've actually not picked it up before, so this is quite scary. I'm going to put it back down before I drop it. I'll let one more photo happen very quickly. OK. But this has been sitting inside our physics museum for all these years. I've got a special kind of case here, which I very gently put it into. By the way, that's why I didn't throw the tennis ball. So, put my clicker over here. So they made this donut in-house, and it's called a donut, and I'm sure you can see why it's called a donut, because it's delicious. And they made this all, again, in-house, using facilities in this department. These are things that even if we still had a workshop, which unfortunately we don't, you simply can't do today. And then, it wasn't enough just to have the one Betatron of 2.8 MeV. You wanted to reach ever higher energies. And so they continued to work on it, eventually got, instead of using a Betatron, they used a very similar setup with a synchrotron. The main difference there is the acceleration technique. For those in the know, it was very much like a synchrotron today, using RF, but much smaller and still with donuts, like the one behind me. And you can see the setup actually looks quite similar to the earlier 2.8 MeV Betatron, but it's a bit larger. Now, this was pioneered by Ed Muirhead, who the museum upstairs is named after, and obviously was a major part of this physics department, because particle accelerators were a major part of this physics department. They were using them for the fundamental research which drove us forward here. And for those attending the reception afterwards, which I imagine are most of us, you can see this donut still in the case up in the physics museum. So if you're wondering how big is this thing, go check out afterwards. If you can't find it, I can guide you to there. It's enamel rather than blown glass, but it is very, very similar. Again, all made here out of parts that were available. And then later on, there was the Siemens Betatron, which is maybe more familiar to many people who would have worked on it while they were students or postdocs or similar here. Went up to a higher energy. Now we kind of doubled from 18 to 35 MeV. But the operating principle of this Betatron is basically identical to the Betatron from 1947, except it's a bit bigger and, let's face it, a little bit better. And there's a little plaque underneath it, which I encourage you to read if you're not before. I've included just part of it here. During this period, experiments performed with this accelerator led to 55 postgraduate degrees and 130 research papers, which is quite a few. So particle accelerators don't just drive forward the basic science, they also drive all of the careers. They train students up from fledgling new people who have no idea how anything works, to well-trained PhD students who know how something works, to postgraduates, and then maybe going on to industry who probably know how the real world works, and sometimes academics who don't really know much at all. But here, there's a focus shift in the physics department at this point. Because before this, accelerators were mostly built in-house, with a hammer and a wrench, and I don't know what else you use to build stuff, especially the blown glass, actually, all in-house. Whereas this Betatron was purchased from Siemens. Now, later on, there was also another Betatron, which was also purchased from Siemens, but only as spare parts. So it would be like a Lego puzzle, putting the pieces together. But this really marks a turning point in the history of accelerators. No longer is this an industry where you can just, fill with things underneath the desk and make something amazing. Instead, you have to work with industry. You have to collaborate beyond your own institution, beyond your own country, beyond your comfort zone, in order to get the results to drive the science that we are continuing to produce here today. And just as an example of the sorts of papers people were writing relating to Betatron, here's basically one random one I found. They're using the Betatron from energies 12 to 33 MeV, so pretty large in that earlier energy scale, a lot more than I could get by throwing my tennis ball. And in that second box there, you can hopefully see I've highlighted that they did this least squares program on the Melbourne University computer CIRAC. This was, to my knowledge, Australia's first computer. It was transferred to Melbourne University after it had lived a long and illustrious life doing various things. And mildly entertainingly, this paper is from 1964, which was the year that CIRAC was decommissioned. So I think this might be one of the last papers that ever used the first computer in Australia. By the way, this CIRAC, this computer, is available to visit. I think it's ScienceWorks, but someone can fact check me on that. But if you're interested in the history of computing, which of course is very deeply related to the history of particle accelerators, because it's very, very hard to work out where your particles go, I thoroughly encourage you to look into more about CIRAC. And so now we're moving on to these various Betatron accelerators. It includes the Lasix one, Muirhead's one, which is partly a Betatron and later a synchrotron, and then these two Siemens Betatrons. And we're kind of starting to move forwards. There was a significant period of overlap with the Pelletron as well, where we had both the protons from the Pelletron and electrons from the Betatron. But of course, we no longer have this facility today. And just to draw a distinction here, on the top we have all these different electrostatic accelerators. These work on that really simple principle, exactly the same as the acceleration in our cathode ray tube of producing our acceleration using just kind of a positive potential and maybe a negative potential depending on quite your setup and shooting your particles through it. But now, what about variable energy proton beams? Because our early Cockcroft-Walton generator was 0.2 MeV, which is kind of low, and also the energy was more or less fixed there, at least in how they were using it. Well, luckily, we have from John Rouse, who put his first name on his thesis, the design study of the variable energy linear accelerator and the variable energy cyclotron. And there's quite an entertaining phrase quite near the start of it, where he just kind of says offhandedly, we were researching into both the linear accelerator and the cyclotron, and we decided to do the cyclotron. Today, this decision would take many months, if not years. There'd be detailed planning studies. There'd be a horrendous amount of paperwork. But back in the 1950s, they could just decide it. And I really want to highlight as well this variable energy cyclotron thing, because there was, before this, no such thing as a variable energy cyclotron. This design, done by John Rouse, was the first design study for a variable energy cyclotron. Now, the Americans might have built it first, but that's, Americans. This was the first one designed. And this is what it looked like, at least this is what the magnets looked like. So the particles would have been circling around in the central region of there, and then above and below it are these two large magnets which are producing the magnetic field which keeps the electrons moving around, protons. His electrons there is protons. This is for protons. No electrons involved here. The protons would have been accelerating, going around in circles, going larger and larger until effectively they just fall out of the machine as they gain enough energy. And here's a top-down view of the same machine in a paper written by John Rouse and David Caro. For those who are involved still in the physics department today, will know David Caro as the name of the building. Or I guess rather, it was named after the person, not the other way around. But his work here was towards the Melbourne University Variable Energy Cyclotron, the very catchy name, MUVEC. And that's what it looked like more or less. This is a top-down view. You can kind of imagine how the thing there labeled a D would fit inside that central region. And it would produce energies from 2 to 12 MeV. So it didn't reach as high energies as the Betatron from earlier, but it did it for protons rather than electrons. And just to get a picture of what this thing looked like, that kind of paddle oar-looking thing in the image there, that is the D. And the long line of something coming off it, that was what enabled them to get the variable energy. They would change the frequency they were using for their acceleration in order to tune the amount of acceleration they would get, essentially. They would also tune the strength of their magnetic field in order to control, essentially, as the electrons were circling around and gaining more and more energy, at what point do they fly out the accelerator. And so we come now to a kind of an interesting and slightly weird thing of the elemental analysis that is possible with protons. Here's just one example paper of the various bits of analysis that were done with MUVEC, where they studied the difference in the elements that were present in unhealthy and healthy eucalyptus leaves. And this all looks like a big blur, but luckily in the paper they included the thing they wanted you to look at, which has particularly this peak around iron and the peak of titanium. And they found, for reasons that were unclear to them, and I don't think anyone ever followed it up, that for the unhealthy eucalyptus leaves, there was much less iron and much less titanium. Now, what they did with these results, I have no idea. But we see that using proton beams, we're able to start looking even though accelerators can get quite large, we can start looking at the individual elements inside something like leaves and use that to make informed scientific decisions. So then we have the lifetime of MUVEC, which is around this period here. So it overlapped quite a bit with the betatrons. There was pretty much no overlap with the Pelletron, largely driven by the fact that the physics department changed building from old physics, well, I guess it was physics at the time, but now it's known as old physics, to where it is now. And so MUVEC ended there. So what happened to the accelerator after it stopped being used? Do we still have it today? It would be great fun if we did still have it, because we have loads of stuff we could use variable energy protons for. But actually, it kind of experienced an entire second life, where the accelerator was transported from here at Melbourne University to Aberdeen in Scotland. And there are some leaflets which I know exist but haven't got the photos for, unfortunately, about the Melbourne-Aberdeen cyclotron project, about how they were raising funds in Aberdeen to bring this cyclotron from Melbourne over to Aberdeen. But eventually they did it. Unfortunately, I have no photos when it was there, but I do have an example of a paper which was written using MUVEC, although they don't call it that anymore, once it was in Aberdeen, on gamma emission imaging in the management of breast disorders. What we're doing here is using positrons, which are annihilating, to produce gamma rays, which are then imaging. But where do we get our positrons from? Well, we need some sort of radioactive something, which essentially you ingest. And how do you make your radioactive something? Well, that's where MUVEC comes in. You bombard a target, you produce some slightly exotic, unstable isotope, someone ingests that, producing positrons and gamma rays, and then they can image them. So this is for medical purposes, and it enables us to say that here is our first foray into medical applications, not close to today, but back in around the 1990s, when MUVEC, an invention from the University of Melbourne, made its way to Scotland. It was there for many years. I think now it's been decommissioned, but I don't know what happened to it. If anyone knows anyone in Aberdeen who you want to ask what happened to MUVEC, then please do let me know, because I'd love to know. Is it just scrap? Is it still there? I have no idea. But now, let's imagine we want something a bit different. We still want protons, but we want a higher current and a lower energy spread for our protons. How are we going to do that? We come back to our earlier concept of electrostatic acceleration. And here we come to our final and kind of most sparky demo, which is over here in the corner with the Van de Graaff generator, which I can touch. No, obviously it's fine, because it's grounded. We checked that beforehand. I didn't almost electrocute myself just now, or did I? So we've already talked about this electrostatic accelerator stuff. And many of you would have seen this before. And so I don't need to, I think, belabor the point of how they work, but I do want to highlight a couple of features of it. First of all, I'm going to put these pieces of foil tins, I guess cupcake tins, on top of it. And then I'll turn on the power here, and I'll make a bit more noise. I'm probably not going to talk over it too much while it's doing stuff. And you can see the belt going up and down, picking up some charge at the bottom and depositing it at the top. And over time, that dome gets charged up. It gives some of the charge to the foil things, and then they fly off. I'm just going to ground it, because if I don't, that's how I do electrocute myself. But I'm not going to, I swear. So we see there kind of the obvious thing, that things that are like charges will repel, and also that we can accumulate charge on the surface of the ball, of the sphere, using this belt. We pick up some charge at the bottom and then deposit it back on the top. And we don't really need to do generating lightning with the ball, but it's kind of fun, so we're going to do it anyway. So it's spinning, it's charging up, There's nowhere for the charge to go. But when I bring this closer, there's our first. I don't know how much you can hear that, but while I'm bringing it closer, it kind of crackles and statics. And it's kind of scary. Oh, we're going to get more. I'll hold this away for a second. Let it build up some more charge. And interestingly, oh, I can hear it, but I don't see it. We saw at least one. Try one more. There we go. Interestingly, this can happen inside the particle accelerator. That background. Again, otherwise I electrocute myself, it's very bad. And so that can happen inside the particle accelerator. In the same way as charge is building up, thanks, Steve. In the same way as charge is building up on the dome, and then sometimes there's lightning, and this lightning, by the way, is, of course, exactly the same as lightning you get from the sky, just a little bit smaller. We can get sparks inside the accelerator, except they don't sound like a little kind of crack. They sound like a massive bang, and it's very scary. And so here's what the accelerator would look like. And for those who are familiar, finally, this is the Pelletron. It has a dome at the top, which looks quite similar to the Van de Graaff dome. Underneath there is the ion source. That's where we get our protons or potentially other ion species from. They're then accelerated downwards through these 5 sections. Each of those sections provides up to 1 megavolt, so in total we're up to 5 megavolts potentially. And you might be wondering, why is this thing called a Pelletron, and why does it sound so much like that bike company? Well, rather than using a single belt which moves continuously, instead it has a charging chain made of lots of individual pellets. So it looks a little like this. It looks exactly like this, because this is part of the chain. And so imagine the Van de Graaff generator, but rather than with the belt with a continuous chain, it's really, really loud. There was a version of this where I thought about maybe trying to showcase the Pelletron in action at the very start of the lecture, and then immediately realized that was a terrible idea, because it was very, very loud in the room at the time, and it would sound terrible. Now, in order to prevent those sparks, which are cool for lightning, bad for your accelerator, it's immersed in a tank of sulfur hexafluoride gas. That tank, I've not got a picture of it here, but that tank is painted this rather fetching shade of green, which is why I've chosen that one here. The gas itself is colorless, odorless, and you just asphyxiate if you try to breathe it in. It's also a terrible greenhouse gas, so you have to make sure it doesn't get in the atmosphere. It goes up to 5 MeV, and we've seen before the pellet chain, that charges it up. And so here are just kind of some shots of walking into the Pelletron lab. As you walk in, you see the control room, vintage. 1975, the machine's installed. Some of the components are from as recent as the early 21st century. But it's almost all still analog. It's almost all read out on oscilloscopes, some of which are definitely older than me. And it's still a bit almost like retro-futuristic. It's quite a cool place to work, really. Then you walk past the control room towards the accelerator itself. And you see this thing. Now, where are the protons or other ions coming from? Well, that whole charging section I showed a moment ago is sitting above. And the protons travel down, go around this curve, and then are shot towards various experiments. And here's just an example kind of looking from the other side. You can see it's going towards here a blue-colored beamline with another red one nearby, and this optical table thing behind it. Here's another view of the same lab. Now we're standing on top of that kind of nozzle trunk-looking thing. And we see a green, a red, and a blue beamline. We'll talk a bit about the things that they do in a moment. And here's a view from the other direction, just so you know that you can stand at either end of the room and still take photographs. And here's looking towards a new beamline, still under construction, which we'll talk about as well in just a moment. But it's exciting times to be working in the Pelletron lab, because it's not just the old existing beamlines, but also new technological innovations happening right now. So we know how it works. Well, we could ask when it works, but hopefully you picked up already. It's been there for about 50 years. It was commissioned, and Beam came out of it in 1975. So here we are 50 years later, celebrating the Pelletron, powering science for 50 years. At this point, I'll also mention before it, there were 2 other electrostatic accelerators, a Van de Graaff, which was very much like that one, and one called the Statitron, which I don't have time to talk about here, but we have many people in the room who spent many years working with these machines. Now, why? That's kind of the big question, is why many people in the audience are here tonight. It's why we're doing this extra July lecture in August. And it's a big part of why the physics department here today is as it is. Now, one of the very early cases where it was used for was, again, looking at nuclear interactions. Here, cross-section of the reaction, I'm not going to try to pronounce that. And we can see here is still that nuclear science experiments relating to that. A lot of time about nuclear photosynthesis, how the stars form, how are they destroyed, and things like that. I'll avoid getting into too much further detail for fear of getting heckled by the experts in the room. And now we can ask, what is the smallest thing we can measure with a machine like this one? and how does that impact science we can do. Now, for reference, my hairs aren't actually that big. My hairs are smaller than that, but we've blown up the cross-section of a human hair, which is about 75 microns across, to be that size. With the Pelletron, using what's known as a nuclear microprobe, which was developed in large part here and then sold around the world, we can measure things as small as that, less than 1 micron across. So imagine how much you could find out about your hair, if you still have it, using something like this nuclear microprobe. And the setup looks a lot like this. It's sitting at the back of the Pelletron lab, kind of quiet and unassuming. You wouldn't even know it was there and what power it has to investigate the world around us if you didn't know how it worked. It can make exquisitely tiny beams, beams that are so small you can't even see them. And what it allows us to do is this elemental mapping again. Remember earlier we saw those eucalyptus leaves, and we had the study of the elements in the entire leaf. So you probably ground up a leaf and then mapped out the elements in there using the proton beam. Well, instead, because now we have such a tiny, tiny beam, we're not looking at the entire leaf, but we can look at the structures inside the leaf. We can see how different elements are present in different parts of the leaf. On the left-hand side, there's kind of all the leaf as a whole, and then you can see, say, the potassium or the silicon in different parts of the leaf, how some elements are taken up in some regions, other elements are maybe randomly distributed. We can see how they're transported through, and use that to inform our understanding not just of whether a leaf is diseased or healthy from its bulk properties, but also from exactly how different elements are present inside of them. Or, for seeds, we can do the same thing. We can see where calcium, silicon, chlorine, nickel, all these elements are present inside a seed. You can see a scale there, 380 microns. That's bigger than a hair, but not by much. And we can see not just where things are, but how much of the different elements are in each of the different parts of the seed. This is what's possible with the elemental mapping capability in the Pelletron lab just over there. We can also do methods such as this ion beam-induced charge in order to discover what's going on in chips we manufacture. And so unfortunately, I don't have enough time to talk about the amazing plethora of science that our quantum computing and quantum sensing programs are powering. All I have time to mention this is one of the methods we use in order to characterize how sensitive and how effective our devices are. And you can see here on the left-hand side, there's an image, an ordinary photograph of a device, and then next to that are features on the device mapped out using this method. This is only possible because we're able to produce such a tiny, focused beam of particles. And so finally, there we come to our kind of last of the things I promised earlier, that with accelerators here at the University of Melbourne, we're also looking at device fabrication, how they work, making them better, making them future-proof, and much more. And I'll be remiss to not mention the thing I did my PhD on with Susie and others, Project Turbo. And again, unfortunately, I don't have nearly enough time to describe all the detail of this really interesting project. The kind of one-line explanation is that we're trying to improve proton therapy by enabling ultra-rapid energy switching. In facilities right now for proton therapy where you treat cancer, one of the main limiting factors is how long it takes to switch the beam energy from one to another. This is limited by the magnets and how they're designed and how they're used. Now here for the Turbo project, which by the way is under construction, we're still building it right now, but ideally we'll be able to transport many different energies of protons all at the same time without adjusting our magnets, and that looks something like this. Now inside there are 5 different beams of protons, from 3 MeV to half an MeV. That covers a huge range of what we can get from the Pelletron. Going around that are magnets. These magnets are bending, steering, focusing the beam in order to get them going around the machine, where they all start together, they kind of wiggle around outwards, and then come together, well, here's the midpoint, and they come together again at the end, right on top of each other. Now obviously, the Pelletron is not a proton therapy machine. The energy is too low, and also there's no way of putting anyone anywhere near that for cancer treatment. But by working on the Turbo project, we can develop key technologies which can improve cancer treatment in the coming years. Watch this space. And finally, I just want to briefly mention a couple more accelerators that are here, just to round out the pack. The Colliatron, which is used for ion implantation for a lot of the quantum devices. And also, we were part of the design and construction of the Australian synchrotron, which powers a huge amount of science. That's not just one other talk I could have given. That's like 7 other talks I could have given about all the different beamlines which are powered by the Australian synchrotron. But now we know it's not even the first Australian synchrotron, because that was the one built in 1950 by Ed Muirhead and his colleagues. But now to get some context on the international picture. Over time, I realize it's probably a bit hard to read on there. Over time, the energy of accelerators has increased, and also their applications in society have grown from just 1 or 2, from this basic nuclear science, to a whole plethora of different ways we can use accelerators. From sterilization of materials, to radiotherapy and security, getting up to higher energy to proton therapy, looking at design of vaccines, archaeology, things like that, to fundamental particle physics, like the Large Hadron Collider and other very large facilities. This is what's been happening in the outside world, essentially, while we've been having all of our little accelerator experiments here in Melbourne. And just for some context, the Pelletron produces about 1 megavolt per meter of acceleration. Modern accelerators with linear accelerators and various structures they use go up to about 10 megavolts per meter, about 10 times faster along the length that you're able to accelerate your particles. But what if we could shrink down our accelerator technology even further? So rather than having a 7-meter tall accelerator, which the Pelletron is, or having a 100-meter long accelerator for our future colliders, what if instead we can make them even smaller? And that's the work we're doing right now in the X Lab, Australia's newest accelerator facility, or at least in Melbourne. This structure can accelerate up to around 100 megavolts per meter. This is a step change in what can be achieved with technology. It makes the accelerator much smaller because you can accelerate the same energy in a smaller distance. However, this is all very difficult. This structure here is on a long-term loan from CERN, who have been developing these things for future collider projects, for the compact linear collider. But if we can make an electron accelerator that's so small, maybe we're not just going to apply it to future colliders. Maybe we'll put it in our hospitals and apply it to medicine for cancer treatment. Maybe we'll use it for sterilization or for device manufacturing. That's really limitless. But again, there's a work going on at the moment, kind of over there, essentially, in the physics department, kind of beneath our feet or just near to beneath our feet, developing novel accelerator technologies in Melbourne. And that brings us to the, I think, last accelerator currently being worked on by the University of Melbourne. And so we can say these very grand statements, and I think Americans are really good at grand statements. The things they can do with a beam of particles: you can shrink a tumor, you can spot suspicious cargo, you can reduce nuclear waste, detect art forgeries, package a Thanksgiving turkey, or discover the secrets of the universe. These are all great and good things that we can do with our particle accelerators, and we should not minimize those things. But let's think back to W.B. Lassick, he of the first name that I could never find out, Smoldering. Now, he was one of the early pioneers of accelerators in this country. When they were looking at these accelerators, they didn't even know what they were going to do with them. One of the other theses I read had this very entertaining paragraph about how they weren't really sure whether they wanted protons or electrons for their nuclear experiments, because at the time, no one really knew what would be better, because no one had explored this space yet. These people were exploring the frontiers of nuclear science at the time, but also of accelerator science. They weren't just these kind of smoldering, perhaps, men wearing black and white suits and ties all the time. These were the cowboys, because they're pushing back the frontiers of accelerators. I did have my own cowboy hat here, although I thought it might be a little bit presumptuous of me to say that I'm one of the cowboys, so I'll take it back off, because it's also now stuck. But these were the cowboys of Australia, at least I would say so. But also, that's not what's true today, because today we are part of collaborative research infrastructure. Today we're part of heavy ion accelerators, where we're collaborating with Canberra, who have the heavy ion accelerator facility, and the ion implantation lab, where the scientific legacy, not just of Melbourne University, but also of the ANU, which I've not had anywhere near enough time to go into, but is massive and terrifying. This legacy is continuing today through collaborations such as heavy ion accelerators, who enable the Pelletron to keep running today. But also, maybe there's one last note about accelerators and how we're using them, but also who uses them. Because it's not just men or cowboys like Lassick in black and white. It's people around us today. And in fact, I want to ask in the room, by a show of hands, unfortunately, who here has worked with Melbourne's particle accelerators at some point in their career? I certainly have. I'm expecting a lot of people down the front to put up their hands, and some people in the audience too who I know have worked with Melbourne's particle accelerators. I can try to make eye contact with some of you because I know you did. And also more generally, we also have people here from the ANU who I won't make put up their hands, but who have worked with the accelerators. These things are all around us. These things are powering the society around us. They're making technological innovation possible. And the University of Melbourne isn't just currently at the forefront of this research, but it always has been. Ever since Cockcroft and Walton's accelerator in 1938, all the way through to today and everything in between. The University of Melbourne Physics Department is powered by particle accelerators. And with that, thank you very much for joining me. Have a great rest of the evening.
Amazing.
Would you like to...
Adam. No, Steve has a job to hold a microphone for the audience.
Sure.
I do have to ask you to put this on for question time.
Yes, this is the question answer.
You can put it on, yes, definitely. But also so that I can look at you and say, smouldering.
I hadn't realized how much I think he is smouldering, so I looked up and was like, hold on a second.
Great term. Just while I'm waiting for questions to come through from the online audience, very happy to take a couple in the room before we move across to our reception. So do wave your hand if you have a question. Right in the front here, a microphone with Steve. Yep, thanks.
I'm curious, did the Manhattan Project use an accelerator, such as the Crofton, or accelerators weren't part of the splitting the atom project at the time?
You might know more about this than I do, actually.
They did. I don't know in intricate detail, but there was a few, yes. And in particular, there was an enormous project to refine uranium that used a version of cyclotrons that was adapted to refine the uranium that Ernest Lawrence was a part of building. I do know that the 184-inch cyclotron that they made at Lawrence Berkeley Lab as well was also co-opted, but I don't know what its role was in that. But it sounds like David can also chat about that at the reception. Stunned. Yes, please, microphone to the middle here. Thank you.
Thank you. I was really interested in how much of the equipment and technology was built here in the early days. Can you talk about those people and those skills and how significant that was to, build this whole legacy of accelerators?
Yeah, I might take off the cowboy hat because it feels very weird. But you can imagine I'm still wearing it. A lot of it was done in-house or built with components they could just find and buy. Thank you, Susie. So for example, that first Betatron, there's a whole description in the paper about how they built the donut. Essentially, they got some Pyrex beakers and then sawed off part of it and clammed them together and then did some glass blowing and made what we had and we saw earlier in the talk. And so really, this is kind of why when I was reading through these theses, this cowboy idea just jumped out because they were doing it all, or a lot of it, really in-house. And for example, in Lassik's thesis, he goes into great detail about not just his contribution, but the contributions of everyone else, of Ed Mearhead, whose name I remember, but there are a whole lot of other ones too. There's a photo on my phone, but I won't get it out now, saying, this person, Mr. whatever, Dr. whatever, Sir whatever, contributed to this, that, and the other parts of the project. And it really was driven by the fact that they knew they wanted to be able to produce these particles here, and they knew roughly how to, but they didn't know the fine details of it. I can also add there, I didn't get a chance to talk about it here, there was a great deal of international collaboration even in those days too. For the design of the Betatron, there are emails back and forth with Donald Kirst about how do we build this donut, how do we coat the interior of it with the right materials, and so on and so forth. And so it wasn't just sitting down in the physics department and thinking really hard and saying, oh, here's how we do it, and then building one. It really was a kind of, I think, a very slow and very painful process. And if you look at their theses, you really see the amount of detail that went into it is just tremendous. All the electronics design, all of the vacuum system design, all the particle beam dynamics. Today, these things would be entire PhDs, or even PhDs may only form part of these projects. Whereas in those days, they were doing it all kind of themselves. It's very scary to read these theses and think, God, how'd they do that?
I'll come over this side. Your hand was up first.
Sorry to be such an idiot, but could you go back to that first demonstration? I'm not sure why that electron beam was blue. I thought it had to be a gas in the cylinder for it to be. Why is it a colour?
I would have thought it's because of the phosphorescent screen in there.
Oh, the phosphorescent screen. Okay.
That's hitting. I'll maybe turn this slightly towards the audience so they can see it again. There's the screen that I was seeing. So if there had been nothing in there, it might be a little bit of a blue glow just because it's not a perfect vacuum, or any sort of glow because it's not a perfect vacuum. But it's really mostly clear, I think, because of the screen it's hitting.
This is going back to the previous question and building things in-house. How much are you hurt with your research program these days by not having workshops in a university?
It's always difficult when you're part of an experimental physics program when you can't build things in-house. Imagine you want to test an idea, and you think, oh yeah, we just need this widget. It's not a complicated widget. It's just a little something which I have no technical skills at all, so I can't do it. And maybe it's a little bit technical. Maybe you need to get something unusual in there and just try it out. With a workshop, that's possible. You can just speak to the people down in the workshop, say, can we put this thing together? You'll work out why your first idea was really stupid. You'll come up with a second idea, a third idea, a fourth idea. You'll collaborate, and then you'll build something. That's not possible without the workshop. Today, what we might do is say, I want to test something out. I guess I'll get it sent off to manufacture somewhere else, maybe in Australia, if it's cheaper, more likely in China. And then there's no collaboration there. There's no engineer telling you what an idiot you are. Of course, you can't build that. It has to be circular, not square, or whatever else. And so I think one of the major losses isn't just that obvious lack of ability to, say, make things in-house, but it's that collaboration between the scientists and the technicians, people in the workshop, who know how to actually build stuff and can make it possible. Without that, we're just kind of throwing darts at the dartboard with our eyes shut and hoping one of them works. So it's not easy, but you learn something new every time your ideas don't work.
You'll be pleased to know we're petitioning to have a workshop again, actively. Was there one more? There was, yeah, I thought I saw another hand over there. Thank you. I'll take this as the last one before we move on. Thanks.
Thanks for the great talk. So what's the future of particles accelerators? Is it the $1 trillion replacement for the Large Hadron Collider, or is it what comes out of the X Lab?
I think if you knew the answer to that question, you wouldn't be sitting in this room. You'd be sitting in a much fancier-looking room, not making decisions. Because it's very difficult to answer what the future of accelerator science will look like. I would say it's all of it, really. These particle accelerators that are being developed, they're not just for a future collider or for proton therapy or for whatever else, or for sterilization, for ion implantation. It's for everything. You can't just develop one branch forward to its peak, neglecting everything else. You need to bring everything forward together, working on it as a whole, with different locations potentially working on different aspects of the accelerator. I have my own personal preferences about the kinds of particle accelerator I hope will be selected as a successor to the Large Hadron Collider, or for the kinds of accelerator we might build in Australia, for example, as a successor to the Australian synchrotron, or even maybe we'll invest in a very large accelerator here, like we do with, say, telescopes. But everyone has their own opinions. Say, for 2 people, there are 10 opinions. So it's very, very difficult to say what the future looks like. But it's, I'd say, an exciting time to be working in accelerator science because there are so many questions. You'd think, surely this field is, approaching 100 years old. Surely by now, all the basics are solved. Surely we can just build machines and turn them on and they'll work. But that's not true. Just at the recent particle accelerator conference Susie mentioned earlier that I went to, there were new ideas about how to make the future colliders 10 times better by improving the injection efficiency, or by changing how we transport particles around. The successor to the Australian synchrotron, if hopefully it gets built, will be significantly better because of the things that have been learned in the time since the first one was designed. So there is no end in sight to accelerator science. And so too, there is no end in sight, I think, to the things that these accelerators can be used for, because I reckon pretty much everyone in here today has a phone which has seen an accelerator at some point. Who knows what the next accelerators will be powering in our everyday lives? I don't know.
I just want to, there was one question online, and I want to give a quick shout out to the folks at the Dalton Institute in the UK who also have a Pelletron and decided to join our event by watching the live stream. So hey folks, quick question from Kay Dewhurst who works there. Are there accelerator manufacturers based in Australia that you work with today? Good question.
It's a work in progress. For example, in fact, in our own department, there is investment from a company called Cyclotech, who design medical radioisotope machines. It's the same application, actually, as what happened to MUVEC when it went to Aberdeen and became Scottish, where they're producing medical radioisotopes for this PET gamma imaging, and there's work being done towards that now by Cyclotech. They already produce these machines, but they're building, actually not sure what they're building, but they're building something new in our own physics department. Other than that, there's a company in New Zealand who provided so many of the magnets which are present in the Australian synchrotron. And then other than that, there are various companies around who use accelerators. Just to name another one to my head is like Stereotech, who do sterilization of cargo coming into the ports using linear accelerators. But I'm not sure how much other active collaboration. Maybe Susie has other ideas about things.
No, you did a more comprehensive job than me because my short answer was no. There aren't any at the moment. There could well be in the future, but most of our industrial collaborators with our research programs are based in other countries. In the US is one example. We're definitely out of time, and there's some drinks and food upstairs, folks. So I'm going to call it there. Could you please give Adam a massive round of applause? Thank you.
Thank you. Thank you.